Assalamu alaikum. Hi guys. Today we're going to talk about the last methods of deflection, which is the deflection of beams, frames, and trusses using the virtual work method. I have divided this up into three parts. Part one is going to talk about the derivation of virtual work. Part two is going to be examples on beam. Part three, examples on frame. And well, I take that back. There's a fourth part which is going to talk about the trusses. So again, that's going to come later, inshallah. So what are energy methods? Now, energy methods are based on the conservation of energy principle, which state that the work done by all the external forces acting on a structure, I'm going to call that UE, is transformed into internal work, or strain energy, I'm going to call that UI. Okay, and that's developed when the structure deforms. So basically what I'm saying that my external work is equal to my internal work. So UE is equal to UI. So let's start with some concepts, and this is going to be the prelude for the derivation of the virtual work. So let's start with the force part. We know that the work usually is equal to force times distance, and I'm going to call that due is equal to f dx if I have an infinitesimal area, an infinitesimal length, I'm sorry. So now if I'm looking at this beam right here, and I'm applying a force P, then I'm getting this deflection delta, with L being the original length. And if I draw the force displacement curve, again, using Hooke's law and assuming linear behavior or linear elastic response, then I'm going to get a straight line. So at force P, I'm getting the deflection delta. Anywhere in between, the relation is P over delta x. Now, if x is my total displacement, then if I do an integration from 0 to x f dx, I'm going to get the total work done by this force. So now I'm going to put, I'm going to substitute for f with the equation p over delta x, which is this one right here. Again, the equation of a straight line. Then the external force is going to be 1/2 p delta. Okay, which is something that we always know. Now here I'm going to do something different. Now I'm going to take the same case, but now having P there. Okay, so P is there. While P is there, I'm going to apply a force F prime. Okay, so when I do that, I'm going to get an extra deflection, and I'm going to call that delta prime. So the total deflection done by the force P and F prime is delta plus delta prime. But I know that P is caused, or delta is caused by P, while delta prime is only caused by F prime. Okay, so this is what I'm talking about if I'm looking at the linear elastic curve. So up to delta, this is done by P. Now the additional deflection of delta prime is caused by F prime. Okay, now let's look at this curve let's look at this figure in detail. So first of all, the total work done by both forces is represented by the triangle A, C, and E. Okay, so both forces, P plus F prime, is giving me that whole triangle, which is triangle again, A, C, and E. Okay, now if I look at the area A, BG, which is this area right here, this is the work done by force P alone. Okay, and we already established that. If I look about the area BCD, which is this area right here, okay, this is the work done by F prime, right? Which will leave me with this area. What does this area represent? Okay, this area, which is the rectangle BDGF, that represents the work done by P, okay, when displaced delta prime caused by F prime. Okay, so think of it, while P was there, there was a movement of delta prime. This speed times delta prime is the work done by P because it was just there. It didn't do any actual work. It was just sitting there. I applied F prime. So it was just riding along for delta prime deflection. So that that energy now, or the external work, sorry, is P times delta prime. Okay, so keep that in mind because we're going to use this in the development of the virtual work, right? So again, just to re-emphasize, this work is divvied up between the work done by P delta, which is again this area right there. Then we got the area by F prime right there. And then we got this area which was due to P just being there, okay, which was simply P delta. Now, if I go back to the moment part, you've noticed that it is very analogous to the work done by the axial force, with the change in equation, of course. Again, instead of having an axial deflection, I'm going to have a rotation, which is d theta. Again, this being my moment, doing the integration from 0 to theta. Again, I'm assuming a linear elastic response. Then my external work is simply 1/2 m times phi. Again, very analogous to the fact of P delta. If I'm going to do the same trick that I did before, while m is still there, applying an additional moment, let's call it m prime, then I'm going to get the rotation phi prime. Then again, this external force is going to be equal to m times phi prime. So this is the work done by m due to the presence of m prime. So now I've figured out what the external work is. Now I'm going to go to the internal work, or simply I'm going to the strain energy. Let me change the color right there. Again, going with the axial force. Now if I have axial force N, and here I have an area for this bar, I know from Hooke's law that the stress is equal to E times epsilon, this being this Young's modulus and this being obviously the strain. Stress is force over area, so then N over area. Then this would be equal, E stays the same. Then delta over L is my strain. Then my delta is simply NL over EA. Now applying the equation for the work, UI is simply 1/2 times N times delta. So now this is going to be N squared L over 2EA. Going to the moment, again, for the moment, I don't have the vertical or horizontal deflection. I have an angular rotation. And we know from the introduction that I gave in the moment area method that d theta is m over ei dx. So dui is simply 1/2 m d theta. Then dui is 1/2. I'm going to replace the d theta with m over ei dx, hence the m square. Then ui is the integration from 0 to L, okay, this right here. Again, x, I'm sorry, I did not clarify, but x is this right here, and here is my dx, and this is my d theta. Again, we talked about this during the moment area method, and by that I mean the relation of d theta equal m over ei dx. So I just carried out the integration. I got my ui 0 to L 1/2 m squared over ei dx. Okay, so let's jump to a simple example. Here I'm going to use the real work that you just figured right out to determine the deflection at C. This is L over 4, and this is 3L over 4. We know that my external work is simply 1/2 PC delta C because we already established that. So now I need to work on my internal. So for that, I need to find out what the moment is. Here I found out the reaction. Again, the reaction is PVA. If I want this one's going to be PVB over L. Hence, this is 3 PC over 4, and this is PC over 4. Now, again, I'm going to have to put up the moment function, and we talked about that at the very beginning of this class. So here I'm using two sections, section AC, and I'm using X this way, and section BC, I'm using X that way. The origin here is A, and the origin down there is B. My limit is from 0 to L over 4, which is this right here, and the limit is from 0 to 3L over 4. My moment is simply, because it's a linear relationship, 3PC over 4 times X, while for section BC it's just 1/4 PC times X. So now I'm going to plug this into the UI equation. I'm taking 1 over 2 EI as a common multiplier. Then from 0 to the fourth of L is going to be 3/4 PCX, and this is the square. Again, 1/2 over EI from 0 to 3/4 of L, and this is 1/4 PCX. And now UI is simply 3L cubed PC over 512 EI. Now using the relation UE is equal to UI, we've shown you this to be PC delta C over 2, and this being 3L cubed PC over 512 EI. Then I can find delta C just simply by being 3PCL cubed over 256 EI. Okay. Now, the problem with this, if I want to find the deflection under C, okay, then I have no problem, right? And we just did it before. So what if I want to find the deflection at D due to PC? And since I don't have a direct relationship between the external force and the internal force, I cannot use that. So let's say I'm having a distributed load. I cannot use that as well, because this is, again, this is only for finding the deflection under the load directly. And hence, this technique is not really comprehensible enough for us. So we need to come up with something different, hence the method of virtual work. So I'm going to start off by using this example right here. And here I want you to find the deflection at D due to PC being located, again, at L over 4, okay, and D is being at L over 2, or at the middle of the beam. So let's do this. I'm going to first remove the load PC. Okay, so if I'm removing the load PC, there is no deflection, there is no nothing. You have this simple beam right there. Then I'm going to apply a force, any force, PD, at the point where the deflection is required. Now, PD to me is an unknown force. Okay, I do not know what this force is. It could be 50 kilonewton, 100 kilonewton. I have no clue. All I'm doing is I'm applying a force at the location where I want my deflection. Okay, so for this particular load, I can find the reaction, which is simply PD over 2, right? And I also can find my moment function, which is simply PDX over 2, right? You cannot dispute that. So for this, let's call this force, unknown force. I'm going to put off on saying imaginary force, but for this force, unknown force that I'm applying, I'm getting this. Again, this is unknown and this is unknown as well, right? So now, here's the trick. While PD is there, I'm going to be reapplying PC. So BD is doing this deflection, okay, and I have no clue what this deflection is, and I don't care, right? Because this deflection, let me put this in green, okay, that's the original beam. So this deflection here, which is caused by PD, okay, I don't know what it is, and frankly, I don't care, right? So now at this position right here, which is what I'm having here, I'm going to reapply PC, right? So now what's happening? By applying PC, I'm getting this deflection delta C, right? And this is due to PC only, okay? Right? And we already established that in the slide before in the example. So we actually do know what delta C is due to PC, okay? But this deflection now, delta D, okay, is what? Simply, what is it? Okay, that is due to PC. But again, this deflection is while PD was sitting on D. So it goes back to, if you remember, the UE prime, where we said it was P times delta prime. And here I'm using the same approach. Okay. Now, the internal forces caused by PC are obviously shear and moment. Okay. I can write both the functions uh, for my moments. Again, this is 3PC over 4. And again, we used that before in the example before. Just a thing here, I'm going to disregard the shear because the influence on the moment is kind of minimal. It's about 1 to 2%, so I'm just gonna ignore it. But it is there. So I'm putting the shear just to let you know that it is there. Okay, and I'm gonna talk more about it in the coming slides. Now, the internal displacement due to PC are again the shear strain and the rotation due to bending, right? So the additional work produced after applying PC is what? Again, this is the PC delta C over 2, and we talked about that. And then this is the P delta times delta D. Okay, again, we said that while PD was there, I reapplied PC, so that extra deflection, it's doing that extra work, which was, if you remember, the rectangular area in the figure that we showed at the beginning of the slides. So having that said, I'm going to go back to the internal forces. Again, I'm getting moment due to PC and small m due to PD, V due to PC and small v due to PD. Again, ignore shear for now. Oh, not even ignore it for now, just ignore it completely. Okay, so now again, after applying PC, the rotation that takes place is d theta. With the same token, I'm getting m d theta over 2 plus m d theta. Okay, again, this is due to PC. So while PD was there, I was able to generate this moment. Then UI is simply the integration from 0 to L md theta over 2 plus small md theta. Now I'm going to remove the theta and put m over EI. All right. So now this is going to become m times m over 2 EI, and then this is going to be small m times m over 2 EI. Then this UI is going to be equal to m squared over 2 EI plus m small times m dx over 2 EI. So now, using the external work is equal to the internal work, then PC over delta PC delta C over 2 plus P delta delta D is going to be equal to this integration here and this integration. Now, we already shown you in the example before that PC delta C over 2 is equal to 0 over Lm squared to EI over dx, which leaves me with P delta PT delta D equal to this integration right here. And since this is a multiplier and this is a function of PD, then PD will cross out with this PD, leaving me to find delta D on its own. And that's why we call BD as the virtual force. Okay. So in general, the external virtual work is equal to the internal virtual work. And this is composed of the internal virtual force times the real external displacement is also equal to the internal virtual force times the real internal displacement. Okay, and we're going to use that abundantly in the example. And here, this is this table. This is the general case. Now, if I am talking about axial force by itself, then this is going to be the integration of small n capital N dx over EA. And we're going to use that abundantly for trusses. This is for the influence of shear. Again, in this class, I'm going to be ignoring that. Usually for beams, it does not materialize itself, but in frames where I have shear and axial force and moment, okay, now the moment we already developed that for you, and which was dx over EI. So for a frame, you should be adding all these three up together, but again, due to the small amount of, or this contribution of the axial and shear in the frame analysis for a moment. I'm going to be ignoring this. So what we are going to use in this class is basically this for both beams and frames. For trusses, we are going to use this equation. Here I'm added, if you want to know it for torsion, then this is the form for finding the torsion part. Okay, if I have a change in temperature, then dl is simply alpha delta T times L. Then again, this is the equation for finding the temperature change. And I will show you that during the examples for truss. So again, this part, I just wanted to show you how we came up with the concept of virtual force. We saw the concept of the conservation of energy. Again, now we are ready to go to part 2 to show you the examples and how I'm going to use this virtual work method to find rotations and deflections. You guys have a very nice day.